All right, hello everyone. We're gonna go over section 2.2, which is going to be on graphs of functions. So in our last section, we learned about what functions are. Now we're gonna go ahead and do graphs of functions. So how do we graph functions? Well, it's really gonna be two main ways. First one by plotting points, old school, just picking values of x, calculating values of y, plotting those points at a graph, and then connecting them all with a line or squiggly line or anything like that. Or using the graphing calculator, which is pretty much going to be the easier part, the easier one almost always. But it is worthwhile to still know how to do both. But starting off with graphing functions by plotting points, we have the first of the definition of the graph of a function. This is from the book. I imagine you probably understand what a graph of a function is, but we're just going to run through the actual definition of it real fast. So, all right, if f is a function that has domain A, the graph of f is the set of ordered pairs, x, comma, f of x. So the ordered pair, x and y values, where your y values are now called f of x, since we're working with functions, while x is in the domain A. This is plotted in a coordinate plane. In other words, the graph of f is the set of all points x, comma, y, such that y is equal to f of x. That is, the graph of x is the graph of the equation y is equal to f of x. All of this just to say a graph is a set of all ordered pairs that correspond to a specific equation. You've seen graphs before. We've graphed things before. This is not new. This is just a fancy definition, basically. So let's move on. So graphing functions by plotting points. We've got a few different types of functions here that are helpful to know going into this. We're going to hear a lot of these words going forward in the class, so it's good to know kind of what is what. So first off, a linear function is a function f of the form f of x is equal to mx plus b. It represents the graph of a line with slope m and y-intercept b. The linear function usually is, well, it's a straight line and then it has varying slopes. So it can look like it's going up or going down, but it's always a straight line. So we have the linear function, in this case, this picture right here, f of x is equal to 2x plus 1. So that's what this line represents. A constant function is a linear function, but its slope is 0, meaning that it's going to be flat. It's going to be a straight horizontal line, and since the slope is 0, that means that x term just goes away, and all you're left with is that constant term there at the end. So this will be a constant function f of x is equal to 3, where you just draw a line at the value of y equals 3. So it's all equal to that y-intercept, that value that is going to go right through the y-axis, which we recognize as being b. So that's what your constant function looks like. It's just a straight line, all the same value, no matter the value of x. Then we have a power function. A power function is a function of the form f of x is equal to x to the power of n, where n is going to be any number that is greater than or equal to 2. So really it's, x to the power of 2 to the power of 3 to the power of 4 to the power of 10 to the power of 100, those kinds of things. So those are power functions. So we see power functions in this first picture right here. We do include a equals 1, but then we have a equals 2, so x to the power of 2, and then x to the power of 3. We have this kind of S-shaped curve here, like a sideways S-shaped curve. And that's what we get when we have x to the power of 3. Then we also have root functions. These are functions of the form f of x is equal to x to the power of 1 over n. So these are going to be functions where you have exponents that are fractions. So we see these in this last graph right over here. We see these are really more of those normal S curves, not the sideways ones. But we see these are going to be S curves with things like 1/2 or 1/3. So x to the power of 1/2 and x to the power of 1/3. They look very similar. It's the only main difference is that they might change a little bit in like steepness in certain areas. But they normally have this kind of S-shaped curve to them. Or in the case of x to the power of 1/2, it just starts at 0. So it would just be from 0 on instead of going into these negative values here. This graph in the middle is dealing with negative exponents, but you don't worry about that just yet, at least. So those were power functions and root functions. Now, if we graph functions with a graphing calculator, learning how to use your graphing calculator is going to be the most helpful thing you could probably do in the class. I've said this before, you are allowed a graphing calculator on exams, although you are not allowed like an online calculator. Like, you can't use Desmos on an exam, but you can use any handheld graphing calculator. So using a graphing calculator, it's a very convenient way to look at a graph, especially in like the crunch time of an exam. If you're just working on homework, Desmos is a great resource, but you will have to know how to actually use that graphing calculator if you want to use it on a test. For instructions on how to use a graphing calculator, honestly, go to YouTube. Google YouTube how to use your calculator. There are lots of different graphing calculators out there, and I've seen a lot of them. I know how to work most of them, but not necessarily all of them. So the best place that you could go to find like specific instructions for your own calculator is going to be the internet, YouTube or Google or something like that. I will show you how to use a TI calculator. They're all about the same. So even though I'll be using the TI-84, they're all relatively the same. It should work about the same for graphing functions. But if you don't have a TI, then it will probably be different, and you should look it up online on how to use it. There are appendices in the back of the book, so I've been told. Not entirely sure. I've heard that you don't have access to them, so that might not even be true. So just internet. Internet is the way to go. Google or YouTube. But there we have it. You can also use Desmos, of course, as a graphing calculator when you have access to the internet, and you can access the internet. If not, handheld calculator is definitely the way to go. So, all right, example 1. With a graphing device, we're going to graph the following functions. A, g of x is equal to x to the power of 3, and b, h of x is equal to the square root of x. So we're going to pull up an online version of a TI calculator, and I'm going to show you what buttons to press in order to graph these functions. So, all right, let's go ahead and do that now. All right, so here's our TI-84 plus Silver Edition. All TIs should look roughly the same. The buttons should be pretty much the same. So we're just going to show kind of what buttons to press here when you want to calculate those different functions. So from our last example there, we have that we want to look at the function x to the power of 3. I believe it was g of x is equal to x to the power of 3, but the actual label of the function really doesn't matter. So what we're going to do if we want to plot this function is that we see this first button kind of up here. It says stat plot, and then there's a y equals that's actually on the button. So you want to press that button that says y equals. So you press that button, and it should bring you up to this screen here. So we have a bunch of y1, y2, y3. These are all different places that you can put different functions and plot them on the same graph. We're not doing that. We're just plotting them each separately. So we're just going to use the y1 space each time. So y1, we're going to go ahead. We're going to put an x to the power of 3. So first we want to put in x. And if we notice, there's a button right here. It says x, t, there's the Greek letters theta and n. It's a bunch of letters, but if you press it, first one to come up is x. That's the one that we want. So we're just going to press that to get x. And if you ever want an exponent, we're going to use this button here that looks like a caret. This little caret. And then you put in whatever exponent you want. So we wanted x to the power of 3. So we want that 3. So we've got x to the power of 3. Now we want to graph it. So back to these buttons here at the top. That last one you see says graph. So from the y equals button and from this screen, we type in our equation. When we're done, we press the button graph. We see it's loading. And there we go. It's done loading. And there it is. We can zoom in if we want. You can zoom in here. We get to press 2. There we go. Press 2. You can zoom in a little bit. You can zoom out if you press 3. You can zoom out again if you'd like. Press 3. So we can zoom in and out to our graph, but this is the general shape that it's going to have. So, all right, now let's do the other one. So we come back to this screen right here. we've got the x, to the power of 3. We're going to get rid of that. We don't want to have multiple graphs on the same coordinate plane right now. So we're going to clear it. And there we go. So now, starting fresh, we want to put in the square root of x. So we're going to have to find the square root function on our calculator. So if we, scan our calculator a bunch of times, we're going to see, oh, there it is. There is a blue root symbol right there. It is above the x squared button, below the x to the power of -1 button. So since it's in blue, that means we need to press the blue button, that one that says second. So the blue button will give you the blue symbol. The green button gives you the green symbol if you want a green symbol on here. So since our radical, it's called the radical, but it's that root symbol. Since we want to use that and it's in blue, we have to press the blue button first. So we press the blue button and then we press that button that corresponds to the root symbol. It's x squared. But so there we have it. We have the radical, and then we're going to put in whatever goes inside of it, which in our case is just x. So we'll put in that x again, and then we want to make sure we finish that parentheses. And there we go. It might look a little funny, but that is what the square root of x looks like in your TI calculator. So all right, we got the function. We got it all typed in. Same thing as before. We want to graph it. We're going to press the button graph. And there we go. We saw it was loading. It's not loading anymore. It's all finished. That's what our graph looks like. We notice there's nothing over here, and that is because, as a reminder, we cannot take the square root of any negative numbers. So our graph is really only defined as this half here with all the positive x values. So this is what our graph of the square root of x would end up looking like. Once again, you can zoom in and out. And we also have this trace function. The trace function just allows you to find values on that line. You can use the back and forth arrows. But just a reminder, trace will not give you an exact value. Trace just finds absolutely random numbers on that line. It's not going to find you, 4 exactly. If you see here, this is 4.04255532. The y value is 2.0106102. Yeah, the x value is 4, the y value is 2. It's not going to tell you that exact number. It is just finding completely random values on that line, meaning that it's showing you big decimal points. It's showing you very big decimal values and whatnot. So definitely please keep that in mind. If you want to find exact values, you really should not be using the trace button. The trace button just kind of allows you to trace your function a little bit, but it by no means gives you exact values. In this case, it did for 0, 0, but that's about it. If you want exact values, you can click on the math button. And it should be not the math button. My bad. The calc button. There we go. That's what it was. Couldn't quite remember. But all right, back to our graph here. We want the calc button. So if we want to do specific things with our graph, we want the calc button. It is the blue version of the trace button. So you just need to press the blue button and then press trace. And then you can find all of these things. You can find a specific value. You can find a 0. You can find a min. You can find a max, an intersect. And then these are for later calc classes. So don't use these two at the bottom. Everything else should be pretty nice to use. So if you want a value in this case, you press enter. Okay, I want x equals 4. Enter. There we go. That gave me an exact value, not trace. So that's what you want to do if you want to find exact values to a specific x value and you want a very specific y value. That would be how you would do it. Don't use trace. Use the calc version. Use the value finder, essentially. So, all right, that's pretty much the rundown for graphing calculators, especially if you have a TI calculator instead of maybe another calculator. You're probably going to be on your own. Once again, look it up, Google it, YouTube, anything like that. But that's kind of the basic rundown for graphing things when using a TI. So, all right, let's head on back over to our lecture. All right, so that wrapped up example 1. We graphed these following functions with our graphing calculator. So now moving on to graphing piecewise defined functions. So we went over what piecewise defined functions were in our last section. Now we want to go into how do we graph these. So piecewise defined function is defined by different formulas in different parts of its domain. So it consists of different pieces or separate pieces of an entire function. So examples, and basically the three main versions of piecewise defined functions are the actual piecewise defined functions. They're going to look like this very first graph that we kind of see here. We see we have a function, and then it just kind of abruptly changes to a different function. And then we even have this value defined down here as well. So we see it kind of has this look to it where maybe it has one function and then it just kind of goes off to another. But they have these unique looks to them normally. Another example would be an absolute value function. So an absolute value function has this V shape to it. And the only way that you get that V shape is really by a piecewise defined function. An absolute value function is a piecewise defined function. It's just that we kind of shortened it into a nice, easy way of looking at it, which is just the two vertical bars outside your X value in this case. But an absolute value function is a piecewise function. Then lastly, we have step functions. They're called step functions because they typically look a little bit like step ladders. Whether or not they're going up or down or up and down many different ways, we see this is kind of what they tend to look like. We see that we have these straight lines that are pretty small, and each one has a defined point on the right-hand side, that defined point being the filled in point, and an undefined point on the left-hand side, a point that is not filled in. So just that empty circle there. And we see that's how every single one of these looks like. And they're always going to have that very same look to them. And they're going up or they're going down. Sometimes they go up and down, but you probably won't really see that. But so this is what a step function typically looks like. And then a little bit later in our lecture, we're going to see how that looks written as an actual equation. But all right, example 2, we're going to go ahead, we're going to sketch the graph of the function. This is a piecewise function. We see that it is two separate functions defined for different values of x, all wrapped up into one function, f of x. So we see that we have f of x is equal to x squared if x is less than or equal to 1. So as long as x is less than or equal to 1, we have the function of x squared. Then we have 2x plus 1 if x is greater than 1. So we have this linear function if x is greater than 1. So we're going to see that kind of abrupt change from looking like a parabola to looking like a line. So, all right, let's go ahead and work on this problem in our notes. All right, so we've got example 2. We have our piecewise function f of x. F of x is x squared for when x is less than or equal to 1, and f of x is 2x plus 1 if x is greater than 1. So we have our coordinate plane here. We want to go ahead, we want to graph our coordinate plane, or we want to graph our function here, our piecewise function. So what we're going to do is that if we're going to do this by hand, because this is difficult to do on a graphing calculator, especially a handheld one. It's hard enough to do in Desmos, definitely very hard on a graphing calculator. So if we want to do this by hand, how we normally graph any function by hand is doing a table of values. We said that normally our table of values should be anywhere between 5 and 7 values to get really a kind of good look at our function here. So just like before, let's go ahead. We're going to just go ahead and pick, let's say, -3 to +3. So we've got another 7 values here. But we're going to do something funny around the value of 1. So let's go ahead and create our table of values. We have x, and instead of writing x and y, we're now going to write x and f of x. Same as before, we're giving more room to the f of x side because we're going to calculate it. And then we're going to pick our values of x. So like we said before, we're going to pick the values of x from -3 to 3. And what we're going to do is that we are going to write 1 twice. And we'll kind of see how this works out when we start writing out these values. So we've got -3, -2, -1, 0, 1. And like we said, we're going to write 1 twice. So we've got 1, 2, 3. Erase a little bit of that there. But all right, so we did this because the values from -3 to 1 are going to be to our first function, x squared. So these values here are x squared. Now the last three values, the 1, 2, and 3, are going to go to the second equation, 2x plus 1. Now, in our equation for 2x plus 1, we don't technically include 1, so we're just going to put a little star next to it. We're going to have to do something special for it when the time comes, but as of right now, we're just going to calculate it how we calculate every other function in this case. So, all right, we want to calculate our table of values. We're going to calculate the first two values for x squared here, and then we're going to fill in the rest of those, and then we'll calculate our values for 2x plus 1 as well. So we have x squared, that is our function, and we have these values of x, -3, -2, -1, 0, and 1. So we're going to plug each one of those values into the function of x squared to get our f of x value. So for starting off, -3, we want to square that value. So we're going to have -3 squared, which if we use our calculator, comes out to the value of 9. Fairly simple. You can use a calculator to do this if you don't feel comfortable. Just remember to put that negative inside the parentheses. So our next value is -2. We've got -2 squared, and -2 squared is equal to 4. So, all right, pretty simple. I'm going to go ahead and fill in the rest. I trust you can all fill in the rest as well. All right, so we filled in the rest of those x squared values. Now let's do the 2x plus 1 values. So we put a star on 1 because we cannot include 1, because our domain for this function is x greater than 1. But we have to remember 1.0001 is greater than 1, but it's almost 1. It's basically 1. So there's all of these really small numbers between the values of 1 and 2 that we have to include. They don't get excluded just because they're not quite 1 and not quite 2. So what we do is that we will calculate that value of our function at 1. And then when we actually graph it, we won't include it by drawing an open circle instead of a closed circle. So that's how we're going to represent that on our graph. But so for calculating our table values, we're going to stick with 1. So we're going to go ahead, plug that into our function. We'll get 2 times 1 plus 1. 2 times 1 is 2, plus 1 is 3. Now we can do this for the next two values, which once again, I trust you can do on your own. So, all right, there we go. We have the rest of our values for that second function there. So we're going to go ahead. Remember, these are all corresponding to ordered pairs. So we're just going to copy these ordered pairs really quickly here, just so it's very clear what we're actually putting on our graphs. So this first one here is -3 and 9. The second is -2 and 4. And I'm going to go ahead and fill in the rest. All right, so here are all of our ordered pairs. Now remember this 0.1, 3, that's not technically included. So we're going to do it a little differently than how we do our other ordered pairs. But so if we want to plot these ordered pairs that we currently have here right now, we can go ahead and do that. So let's go ahead. First, we're plotting -3, 9. That's probably going to be right about here. Then we have -2, 4. Should probably be right around here. Then we have -1 and 1, right about there. 0, 0. And then we have 1 and 1. So this wraps up our graph for x squared. Since we know that this is what our graph of x squared looks like, we can connect all of these values right now. Let's go ahead and do that. We can connect these values. And then we can add that little arrow on to say that it continues in the negative direction as well. We just don't want to write anymore. So here is our graph of x squared. So that's x squared right there. Now we want to go ahead and do 2x plus 1. And so we're going to start at the point 1, 3. But remember, we can't actually include it. So we're going to find our point 1, 3 on our graph. And we draw an open circle instead of a point, a filled-in point. So once we have that open circle there, we can go ahead, plot the rest of our points normally. So our point 2, 5 will be normal, will be right around here. And 3, 7 will be normal as well. And now we know these are the values of 2x plus 1 as well. So we can connect these two. And we put a little arrow to show that it's going to continue on in the other direction as well there. So this graph right here is 2x plus 1. So what we have here is our piecewise function. All right, I changed half the graph from green to red just because I think it looks better visually. But so that was x squared, corresponds a little bit better now. So that was x squared, and then we had the 2x plus 1 defined on the values of x that we had defined from our piecewise function. So this is our piecewise function. All of this represents f of x. That is our graph f of x. It is in purple because of the combination of the blue and red graphs that we see below there. So this whole thing is the graph of f of x, even though we did color code them with the two separate functions, which are defined in separate areas. So coming back to the point 1, 3 that corresponded to the graph of 2x plus 1. This point here that got that open circle, that point has to have an open circle because our function was defined already for when x was equal to 1. It was defined under x squared. So the graph of x squared got that point. It got to have that filled in point. But our other function, although it was defined for super close to 1, it didn't actually get 1, so that's why it had to have the open circle. You can never have 2 points that are both defined. If you ever have a piecewise function like this, and you have, that 1x value, and both of your graphs are going to be defined or somewhat defined on that point, they cannot be both filled in. One has to be an open circle and the other one can be filled in, just because for functions, you cannot have 2 different y values defined for a single x value. So that's typically why we see this type of piecewise function being depicted when it comes to the graphs of piecewise functions. So, all right, that finishes up example 2 here. So let's go ahead and head back over to our lecture. All right, that was example 2. So moving on with the details of graphing piecewise defined functions. Now we've talked most about these things that are on this slide here. So now we are just really driving these details home. So when graphing values of your independent variable, which is typically x, it includes inequalities. So that's the less than or equal to. I wrote that, okay, greater than or equal to. Got confused there for a second. So these are all the 4 different types of inequalities. We have strict inequalities, the ones without the lines underneath, those are strictly less than or strictly greater than. And then we have the less than or equal to's or greater than or equal to's. That's where you have the line underneath. It means that you get to include that value. Whereas for strict inequalities, you do not include that value. So that point on the graph at the inequality would look like one of the two. So if you have a strict inequality, meaning that you do not include that value, it gets an open circle. So it gets the open dot instead of a filled in dot. And an open circle if the inequality is strictly less than or strictly greater than, which is how we saw in our last example there with the 2x plus 1. That graph is copied here as well. So we saw that f of x was equal to 2x plus 1 when x was greater than 1. It had a strict inequality, so that graph got an open circle. Now, we have a closed circle if the inequality is less than or equal to, or greater than or equal to. So on our graph here for f of x is equal to x squared if x is less than or equal to 1. So we see that this was the function that had the closed circle because it had the inequality that included 1. So inclusions, these are closed circles. They have, less than or equal to or greater than or equal to. Open circles are not included and they have the strictly less than or strictly greater than inequalities. So last kind of idea here, a function is called continuous if it doesn't have any breaks or holes. So if we look at our function right here, it has a break. We say that our function was, defined, and then there was this chunk where there just really wasn't anything there, and then it continued on kind of higher up. So this function here had a break in the graph. So if you want to imagine continuity, like you're sitting on a little roller coaster on your graph. If you are sitting on a little roller coaster on your graph and you are going down this roller coaster, you're having the greatest time of your life. This is so exciting. I love roller coasters. And then you just fly right off. There was a break. It's not continuous. If your function is continuous, that means that you could ride a little tiny roller coaster on your graph and you would not have fear of death. But here we see it is not continuous, since our little roller coaster would just fly right off that graph there and we would all, perish. So that's why we say it's continuous. Also, same idea if you have a hole in your graph, meaning that it is defined, but there is just an open hole right in the middle of your graph there, you would fall through the hole as well. That also means it is not continuous. So just a fun little example on what makes a function continuous and what makes it not continuous. So, all right, on to our next example. We are now given the graph of a function. We want to write this function in form of a piecewise function. So we're given the graph, we're given, what the graph is representing. We want to take this graph and instead write it or turn it into a piecewise function. So let's go ahead and continue this on in our notes. All right, so here we are, example 3. We have the absolute value of x here. We have the graph. We have the function itself where we just have f of x is equal to the absolute value of x. But the absolute value of x actually is just a really shortened version of the piecewise function. So we are instead defining the piecewise function that would go along with absolute value of x. So we have f of x is equal to, and we have 3 different types of functions listed here. We want to list a function for if x is greater than 0. We want to list a function if x is equal to 0. And we want to list a function if x is less than 0. So looking at our graph here, let's go with the middle one. If x is equal to 0, what is our graph? What is our f of x value? What is our function value? And if we look at our graph, we see our graph is defined at the point 0, 0. This right here is 0, 0, which means that when x is 0, f of x is also 0. So if we want to define our function for blank, if x is equal to 0, the only result that can go there is 0. Our function has to be 0 if x is 0. So that was one part that we were able to work on. Now let's do the first. We see f of x is equal to blank if x is greater than 0. So if we look at our function here, and I did redraw this is hand drawn. It's not entirely perfect, but I must say it's pretty good. So all right, we have blank if x is greater than 0. If we know that x is greater than 0, we can just start by picking some random value of x. Well, let's just say, what's f of x when x is 1. So if we look at our graph here and we find when x is 1, we can go ahead and kind of make a dotted line up to our function, and we see that our function when x is 1, y or f of x is also 1. Same thing for 2. When x is 2, f of x is 2. And when x is 3, f of x is 3. So this means that whatever x is, our function will have to match. So if x is 1, f of x would be 1. And if x were 2, f of x would be 2. And if x were 3, f of x would be 3. So when we write that, we would say that f of x was just equal to x. It is also a line with the y-intercept of 0 and a slope of 1, meaning that our function here would be f of x or y was equal to 1x plus 0, which simplifies down to just x anyway. So when x is greater than 0, we have f of x is equal to x. It's going to match. So now on to the last one here. This one is just slightly trickier, but just barely. So we say f of x is equal to blank if x is less than 0. If we follow along with the idea that we took before and said x, if x was less than 0, that means that it would match. So if we took a number less than 0, like -1, f of x or y would be -1. But that's not what we see here. If x were, say, -1, f of x is +1. And if x were -2, f of x would be +2. And if f of x were -3, f of x would be 3. So we see it's the same number, but it's not negative, it's positive instead. So if we wanted a function that would take the same number, but change its sign, we would have to make this -x. Because if x is inherently already negative, when we plug this into our function, it would have a double negative, which would come out to just a positive x. So another way we could look at this too would be that for x less than 0, we have a line with a negative slope of 1 with a y-intercept of 0. So in our slope-intercept form, we would have, f of x or y was equal to -1x plus 0, which simplifies to -x. So this is our function here, our piecewise function for the absolute value of x. And there are actually many different ways to actually write this function. I personally like this one just because I think it is a little bit more clear. You're kind of defining every unique value. But there are different ways to actually write your piecewise function of an absolute value like this. But this was just a practice here on kind of how to go in the opposite direction, how to look at a piecewise function and figure out its actual function equations that go in the piecewise function, as opposed to plotting points to getting the graph. You want to go from the graph to the actual function. So, all right, that wraps up number 3 here. So let's go ahead and go back to our lecture. All right, we just finished up example 3. So another example, here we go, example 4. This will be our last example, and then we just have 1 or 2 slides left. So example 4, we want to graph the function based on the given problem and corresponding table of values. So we have a table of values in this case, and we want to graph the function from a table of values instead of an actual equation. So here we go. Our word problem here is a global data plan costs $25 a month for the first 100 megabytes and $20 for each additional 100 megabytes or any portion thereof. Draw a graph of the cost C in dollars as a function of the number of megabytes X used per month. So we have our table of values here, and when we go ahead, when we draw out this function, since we have our table of values, we see X is defined for certain intervals, and then we have a value of C of X on those intervals. we have a piecewise function on our hands here. So let's go ahead and draw this out in our notes. All right, so here we go, example 4. I wrote down the most important parts of our last slide there. So we have the cost versus the values of x. So our cost, we said, was calculated by, our phone plan here with a base cost of $25, which includes anywhere between 0 and 100 megabytes. And for every 100 megabytes extra, you pay an extra $20. So we paid $25. For any megabytes between 0 and 100, we pay 45. For any megabytes between 100 and 200, we pay 65. For any megabytes between 200 and 300, and we pay $85 for any megabytes between 300 and 400, and the list goes on and on. So when we graph this, this is a piecewise function. This whole function is the function of cost defined for different areas or values of x. So, starting with our first interval, we have the interval of x between 0 and 100. The cost is $25, no matter if you spend, 1 megabyte, 50 megabytes, or 100 megabytes. So for all the values between 0 and 100, the cost is the same. The only difference here is that we can include 100, but we are assuming that nobody's actually spending 0. We're assuming that you're actually using this phone, so you would spend more than 0, even if it's 0.1. So we're not including 0. We have to put an open circle at 0 and a closed one at 100. So at the value of c of x is 25, this is c of x, this is x. So at the value of 25, when x is 0, we're going to go ahead and put an open circle right there. So we have an open circle, and then we're going to have a closed circle at 100. And now what we're going to do, since the cost is the same for any value in between, is we're going to draw a line, just like that. So this represents the cost being $25 on the interval between 0 and 100, where we don't include 0 and we do include 100. So now we can go on to our next line here. We have that the cost is 45 when we spend anywhere between 100 and 200 megabytes, but we're not including 100 because we included 100 in our last interval. So we can't include 100 again because we already included it. So we want to do the same thing. At the value of c of x being 45, we're going to draw an open circle when x is 100 and a closed circle when x is 200. So we'll find 45 on the graph. It's probably right about here, 45. So we're going to go ahead. We're going to draw an open circle at 100 and a closed one at 200. And just like before, the value of our phone bill, our cost here, is $45 no matter where you landed in between 100 and 200. So we draw a straight line. You can kind of see where we're going with this. We're going to do this 2 more times. So our next line here is that we are paying $65 for a phone plan of megabytes between $200 and $300. We do not include 200 because we included 200 in our $45 phone bill, but we get to include 300 this time. So at about 65, which is, probably somewhere right in here, 65. At the value of 65, we're going to go ahead and we're going to put an open circle at x equals 200 and a closed at x equals 300. So right about here, open circle at 200, a closed circle at 300, and we draw the line in between. All right, one last time here. Now we have that last line, 85. So we're paying $85 for spending anywhere between 300 and 400 megabytes. We saw that 300 was included in our last interval, so it cannot be included in this interval. But we get to include 400 instead. So at the value of c of x is 85, which is, once again, probably like we're right here, So at the c of x value of 85, we're going to go ahead, draw an open circle at x equals 300 and a closed one at x equals 400. So at x equals 385, we draw an open circle and a closed one at 400. And then, just like every other time, we're going to connect those with a line. So we can imagine that this goes on and on. For people that spend more and more megabytes, on their phone plans and whatnot, this can continue on for as long as, well, probably the phone company will allow it. So what we're going to do, because we definitely don't want to graph all of those, is that we're just going to put 3 dots going up kind of in that diagonal fashion. We're going to say, yeah, this continues on, but I'm tired of this and I don't want to draw anymore. So there we have it. This was a step function. This was that function that kind of looked like the ladder. And now we kind of see how this would arise in kind of a real life application or real life example, and how we would have to do a step function to represent a piecewise function in a real life, situation. So, all right, that wraps up example 4. Let's go ahead and head back on over to our lecture. All right, that was example 4 here. So let's go ahead and finish up our section. The last concept that we have here is the vertical line test. What graphs actually represent functions? Like we've mentioned before, we talked about what can be allowed in graphs of functions and what can't. So the vertical line test will tell us when a function is actually allowed. The vertical line test states that a curve in the coordinate plane is the graph of a function if and only if, being just like strictly, no vertical line intersects the curve more than once. So your vertical line is always staying vertical, and you're going to just move it across your screen. When you move it across the coordinate plane, if that vertical line crosses your graph twice in one spot, it is not a function, because that means that it has 2 different y values defined for a single x value. And that is what is not allowed. A function cannot assign 2 different dependent values to a single independent value. That's why we always had to have the one filled in dot and the one filled dot, or the one filled in and the one not filled in on our graphs and whatnot. If we had to have 2 y values for the same x value, that is the one kind of way that we could actually get around that. But other than that, we cannot have 2 different y values defined for a single x value. So that's why we use the vertical line test. The vertical line test is just kind of a really simple, easy way to just check really fast. You can use anything that represents a vertical line, something like a pen. You can actually have a ruler, side of your phone. I mean, really anything that represents a vertical line. So we've got 4 examples here. For example A, we see it's a circle or an oval here. That vertical line does cross it twice, which means that it is not a function. This means that that equation of a circle that we learned about a section or 2 ago, not a function, only an equation. Then we have a graph like B. We have this graph here. If we used a vertical line, it would never actually cross 2 y values at 1 x value, so it is good. It passes the vertical line test. For part C, even though it looks a little strange, same thing, vertical line would not pass 2 y values for the same x value, so this one passes the vertical line test. And the last one here, last part D, we have this funky backward S-shaped looking curve here. And yes, if we draw a vertical line, we see it's going to cross just not twice, but 1, 2, 3 times. It would have 3 separate y values for 1 x value. So it is definitely not a function in that case. So using the vertical line test is definitely a quick and easy way to check if a graph represents a function. A little tougher if you actually just have an equation versus a graph, but if you just have a graph, very easy to use. So lastly here, what equations actually represent functions? So we looked at, how to tell from a graph. Now, how to tell from an equation. So an equation will represent a function if the equation defines a rule that gives one value of y for every value of x. Basically, we're saying that it just cannot give multiple. So we can express this rule as function notation, meaning that we would have f of x is equal to something. If we wrote f of x is equal to some expression, we can assume that that's a function. and that it's not an equation, that it passes all of the function rules and whatnot. Otherwise, if you do have an equation that is actually not a function, we can express that in just equation form. This case, it is also a function. It's not a function, but typically if we kind of switch over to this y instead of using f of x, definitely some cause for some suspicion. Maybe work some stuff out, use a vertical line test, stuff like that. But so we can use equation form when we want to represent equations, functions when we want to use functions. So a really common equation that doesn't define a function is the equation of a circle. Like how we said before, the equation gives you two values of y for any given value of x. So that's probably the most common one you're going to run into. Can't imagine very many other examples of functions or equations that are not functions other than the equation of the circle. You're really not going to run into any other types of functions or formulas other than the equation of the circle. But a good way to look at it if you don't actually have a graph is that if you solve your function for y and you get this plus minus sign, it's not a function because that would be two different values. So basically that's what you're looking for. You can't have y is equal to some plus or minus value. That would be two separate values. You just can't have that. So if you want to look for it algebraically, that would be one way to do it as well. So that kind of gives you an idea of what equations represent functions. But as a rule of thumb, from here on out, we're mostly working with functions. It's not going to be as much of a concern of are equations functions. We're just assuming it's functions from here on out unless, stated otherwise. But all right, that finishes up section 2.2. So from section 2.2, we learned how to graph functions by plotting points and using graphing calculators, how to graph piecewise functions, determining which graphs represent functions by using the vertical line test, and determining which equations represent functions. So, all right, that wraps up section 2.2, and I'll see you again in the next section.